Thank you, Richard. So I'm gonna, as Richard said, I'm gonna talk to you about a system we developed a number of years ago. It wasn't actually 5 years ago. It was like more like 3 years ago for a bus fleet system based on OSGi. But first, so I'm going to do first a quick introduction to Makewave, who we are. I'm going to introduce you to what a vehicle fleet system is. I'm not sure if everybody here is familiar with that, but that will be very brief. We'll speak a bit about how we can actually manage IoT gateways with Ubicore, which is our remote management system. Say a few words about the system architecture actually used, and round off with some of the lessons we learned during these developments. So, first of all, Makewave. We do middleware. We are basically the company that makes the Knopflerfish OSGi, which is an OSGi stack. We also make Ubicore, which is a remote management system. In addition to that, we say global services. We basically do consulting in this area for various customers around the world. We've been around in the OSGi space for quite some time. We're actually, the roots of Makewave was called Gatespace, and we were founded in 1999. And we were assigned the task to develop the first commercial platform for Ericsson's e-box system, and this was actually back in 1998, year 2000. And we are very active within OSGi. I have the fancy title VP EMEA of the OSGi Alliance. So if you want to know more about the OSGi itself, you're more than happy to come and ask me questions. We are located in Gothenburg, Sweden. And as I said previously, we are perhaps best known in the OSGi world as the company that makes Knopflerfish, which is one of the OSGi stack. It's open source. We also make Ubicore, which is a remote management system for edge devices, and I will speak about that much more in detail later. So, introducing you to vehicle fleet system. What is a vehicle fleet system? Well, basically it's you have a large fleet of some kind of vehicles. In this case, it's buses, it could be trams, it could be trains, it could be virtually anything. Anything that typically resolves around either public transport or transporting goods. These systems are then typically connected to a backend server, or in these days, a cloud system of some kind. Characteristics of a fleet system. What makes a fleet system perhaps somewhat different compared to other systems in the IoT space are that, first of all, the edge devices, they move around. They typically don't have a fixed location. They are inside the vehicle, so per definition, they move around. Furthermore, edge devices are rarely always on in the world of fleet systems. When you turn off the bus or stop the train at night, you typically turn off your system. That's typically how you do it. That's how it's been wired inside the buses. Furthermore, the edge devices are not always connected. This may sound strange, but if you run a bus in some local remote area, it could be out in the countryside in Sweden, there are some certain spots that aren't connected. So you cannot assume that your system is always connected. Furthermore, when they are connected, the speed of the connection may be quite different depending on if you have actually 4G, or if it drops down to 3G, or even goes back to edge connection, which also can happen if you are in a rural area somewhere. And that can also impact the transmission cost. It might not necessarily do that. It also, of course, depends on the tariff plan you've set up with your company operating your internet traffic over wireless networks. Often also there are several edge devices within the same vehicle, but most typically only one of them actually have a wired area connection. You only put in one data modem in one of the gateways because that reduces costs. Furthermore, typically you want them to easily find and detect each other inside the vehicle. So if you have, in this case, a bus, here we have 5 onboard edge devices all running OSGi. You typically assign one of them as the communication gateway. This is the gateway that's going to communicate to the outside world, and it has some kind of wide area connection. That is then connected to the backend server or cloud server. So the physical connection goes through there, but then the logical connection, of course, goes directly from the from every edge device directly to its corresponding server. You typically then, in a bus system for local transportation, have a number of validators. Validators is the thing that you show your smart card against, and it uses a beep, and then you're allowed to enter the bus. You have at least 2 of them, you may have 4 of them, or maybe even have 6 of them on board on one bus. There is very often also something called a driver's console. That is the console that the driver has with information about timetables, etc. And that is typically connected to something called FMS, which is the equivalent of the CAN bus, if you're familiar with that. That's the internal bus system of most of vehicles today. So FMS is the CAN dialect for buses, at least in Europe. In the US, they have a different dialect to complicate things further. Furthermore, common requirements you see on a fleet of moving IoT gateways are the following. Software updates and software reconfigurations are quite common. Every 6 months there's a new timetable. You change from winter timetable to summer timetable. You need to deploy a complete new set of configurations. You also change to where the bus actually stops, or you change to how you apply the tariffing, how much should it actually cost to validate your ticket on this bus. Also, since this also involves money transaction, and this is a really crucial services, you always need to verify where the software came from when you download a new version of the software. You just don't pick it off random site off the internet. You only work with signed software here. Furthermore, a software update should never ever be allowed to fail. You have 5,000 buses remotely distributed over the country. You want to push out your winter timetable, and you want to make sure that doesn't fail. And if something goes wrong, you should always be able to go back to the previous state. So you don't want to end up in a state where your device is non-responding, because then you have to send out an engineer in the field with his laptop, connect to the device locally, and that is very costly and time-consuming for the company operating the buses. So always test and verify what you're actually going to download. So a lot of time spent in this world is on testing and verifying that what this new version of the software we're going to deploy actually works on our validators and in-car driver's console, etc., etc. Finally, usually or quite often, updates should happen at a fixed time for all gateways. So the morning on, I'm not sure which example I took here. The morning of the 1st of November, the new tariff plan should be in place. So when you boot up to the bus in the morning, the IoT gateway starts up, then it should be running that latest version. And so it's not, you cannot really have a rolling update. You update them one by one. So you really have to push out everything. And what you typically then do is that you make sure that this new version is installed on all your IoT gateways beforehand. So you can you can start a week before. You start to push out the new version. You know that this new version is out there on all the buses, and then you can actually make the upgrade to the new version. Furthermore, provisioning, meaning download services, should only happen when connected to a Wi-Fi hotspot, not 3G or 4G. So at the bus garage or some bus stops, downtown locations, etc., they typically put up hotspots with excellent Wi-Fi connection. Because updating thousands of buses over 4G may be it's a big cost saver for them. It depends a bit about the tariff plans. Costs are dropping, but still it's a huge cost saver for them if they can do this at hotspots. Since you have typically several gateways inside or several edge devices inside the same vehicle, you want to have a local bundle cache for the vehicle. So if you have 5 gateways inside the vehicle, you don't want to go out and download it 5 times over the internet to the actual bus. You download it once, and then you distribute it locally inside the vehicle. So what kind of services do we actually implement using OSGi? Well, the most common one is, of course, validation. You validate your ticket at the ticket machine. You can also, in some cases, purchase tickets. You have a driver console informing the driver what is going on in the system. Another important aspect is maintenance and monitoring. You can actually do maintenance of the buses. You do monitoring of the buses. You get all the information from the FMS bus, the bus of the bus. You of course do tracking. Where is this bus right now? Is it late? You check that against the timetable. You send it up to the central server that keeps track of all the buses. And of course you can provide passenger information. This could just be as simple as driving the little signage you see in the roof in the bus saying the next stop will be this stop, and you can umsteigen nach whatever you want to go. Change the bus to change here for lines, etc., etc. So that was the quick introduction to what a bus fleet system is about. Now I'm going to say a few words about Ubicore, which is the remote management system we have at Makewave. So Ubicore is a system for managing edge devices. You can do device management, service management, user management, and configuration management, and we do all the provisioning down to the edge devices. It's not limited to vehicles. So from a Makewave perspective, it's just an IoT gateway. It could be inside a vehicle, it could be a home gateway, it could be inside some industrial equipment like a printer or some other type of machinery. From an OSGi perspective, we don't really care about that. The typical scenario, this is actually a home gateway scenario. I'm not going to spend too much time about it, but you have the edge device, in this case a home gateway running Knopflerfish. You have the Ubicore, which is the provisioning server that is managing and controlling the gateway itself. Up there you see a picture of the gateway, and on top you see the three so-called end-user applications or bundles. That's, in this case, just three examples: energy management, home security, and health monitoring. They are then directly communicating with their corresponding back-end servers. And in the home gateway use case, you might have a user logged on, and he can typically use his, either his browser to surf onto the home gateway, use an app, and there he sees information about his home. So these are the kind of systems that we developed at Makewave, or helped to develop Makewave. So Ubicore, it's designed for managing embedded edge devices. It can have an end user logged on. That's more the typical home gateway scenario. But it can also be completely without an end user involved whatsoever. It's a completely black box sitting out in the field monitoring some kind of machinery or device. The design principle we have with Ubicore is also that Ubicore knows exactly which bundles are installed where, what configurations has been sent where, and which state the bundles are in, if they're installed or if they are started. Ubicore also pre-resolves everything beforehand, so we make sure that what actually is going to be sent down actually can resolve. It might go wrong for other reasons in the edge device, of course, but it's not that we push out one bundle, start resolving and pull down everything from the edge device. Instead, we pre-resolve it, calculate, okay, this is the bundles you're actually going to need in this software package, package them up in one single package, and make sure they download it to the edge device. And this is very important, especially in the IT world, where such packages beforehand can be tested, verified, and signed. This is a signed package, signed off by Ubicore. This is something you can trust on the edge device. This you can install, this you can run. So you can say that Ubicore is in control. Ubicore really sends down a recipe to the edge device saying, this is the bundles you should start. Please do that for me. And on the edge device, you have a management agent that is responsible for performing all these management tasks that the Ubicore server has requested. The Ubicore agent, of course, then reports back status to the server, if the operation went successfully, or if something went wrong, it can report back an error. We have further concepts in Ubicore which we have defined by ourselves. We have something called the OSGi firmware, and the OSGi firmware is really, it's the framework and the core set of bundles that makes the edge device manageable. It's a kind of, you need at least these things to run to even be able to speak to Ubicore and to receive commands back. Then we have something we call service application, and that's really just a grouping function. So typically you would group together a set of bundles that perform some kind of logical function or service together and package them together and say this is a service application that deals with this, whatever it may be. As I said before, we always pre-resolve on the server, and we sign the firmwares, the bundles, and the configurations. So everything that goes down to the agent is signed. It's optional to do signing, of course, but that's what in a real live system, that is how you would typically do it. I mentioned before the management agent running on the edge device. That's responsible for all the management operations. You can see it's the field agent for Ubicore. It does what Ubicore tells it to do. It has a local edge device bundle cache or a repository. So it has, if you want to pre-install something downloaded beforehand, it has a cache or repository with current versions, previous versions, and next versions of bundles. Also, in most systems, it's the management agent that always initiates or establishes the connection with Ubicore. Most often, you're out there in the field somewhere. You typically don't know the IP address of the edge device. So instead, you configure your system such that the agent or the edge devices connect to Ubicore at the regular interval, sending a ping, here I am, do you have any operations for me? And then the response back you get out, and you either get back, now everything is fine, or please install the following bundles. There is also a management agent API, so you may in certain circumstances want to have some edge device business logic that want to take decisions based on what to do when you upgrade or downgrade. And this is something that the customer of ours, the company running a system based on Ubicore, will develop themselves. So they can take decisions on, now we should upgrade, now we should downgrade, for instance. And through that management agent API, you can also do local installations and local management of the platform. So if something goes wrong and the service technician comes out to the bus, he can connect to it through his PC and actually do upgrades or downgrades or fixes or change configurations, etc. So the OSGi firmware, it's really a definition. You can see a piece of XML up there. It says these are the components you should run. There's also configurations included there, and as I said previously, it's the core set of bundles and bundle configurations you need to run to become manageable. It's packed together as a single jar, and when it starts up, you have an OSGi platform that actually can talk to Ubicore and receive commands from Ubicore. You can do firmware updates. So you send down a new version of the firmware, where a few of the components has been changed. You actually provision them down in a package. They get sent down to the edge device. They will be first downloaded, and when either Ubicore or the management agent, someone uses the management agent API locally, says it's time to upgrade, you will make a switch over to the new version. Depending on the components you update, Ubicore or the management agent will decide or calculate, do I need to restart the framework, or do I even need to restart the VM? You can signal that out, that this restart actually requires a restart of the VM. And that typically involves, if you use some, as most of you probably know, there are some things that are singletons in Java. And if you change a configuration for them or change something for them, you need to restart the VM for them to become effective. So I think I said most of this. The firmware versions can be installed, they can be running, they can be failed. When you start up a new firmware, it will be marked as failed if any of the start methods would throw an exception. And in this case, the management agent will abort that operation and try to restart the previous good version. And a version is considered good if it has successively started at least once. There's also a basic initial version present, and you can regard that or see it as a factory settings versions. This is, if everything go, I mean, if you have a home gateway or router, you usually have a push button saying, okay, take me back to factory settings, something is wrong. And this is the equivalent of that. This is the initial set of bundles you had on the device. You can keep any number of firmware versions on the edge device, but you typically have the factory settings, the previous good version, and the current versions are running. And all of these bundles are stored in a bundled cache, and I will explain that in a few minutes. I mentioned also previously we have something called service applications, and service applications is really a grouping of bundles. We group something together. It makes it easier to talk about them or to mention. This is the validation application, and that consists maybe of, I don't know, 5, 10, 15 different bundles. And you can almost regard them as an app. You can think of them as an app. It's an app you download on your edge device, and they run. They run on top of the firmware. They don't really run on top of the firmware. Of course, they run in the same VM together with everything else, but you can perhaps conceptually see them as something that runs on top of the firmware. They make use of all the services that are present in the firmware. A bundle can also exist in multiple service applications, so they can actually overlap. In this case, we have 2 different service apps, XYZ and ABC, and both of them actually include bundle Z. Bundle Z will only be started once. So we do some internal bookkeeping to make sure that when you add service app, this bundle first time, it gets installed. When you add this one, it doesn't get installed. It's already there. If you then remove this service app, it will keep track that, okay, this bundle here is actually referenced by that service app, so we will actually keep it. We don't use subsystems or anything like that to really isolate them. That's something we have looked at and discussed, but right now we run everything in the same kind of scope. There's a bundle cache. This is a local bundle cache on the edge device. You can call it a cache, you can call it a repository. And that's a summary of all the bundles that are present on the device. You have the firmware bundles there, and you have all the service app bundles there. And the firmware definitions and the service app definitions, they point into this bundle caching. I'm using this version, I'm using this version. And they are stored in something called a device management tree. This is actually an OSGi specified function. I'm not sure if it's an old thing. It's been around for quite a while, but for these kind of things, it was designed for these kind of things, and it's quite useful actually. So, looking at an actual system architecture, we have a backend system with Ubicore, a number of different servers. There's a driver server, there's a validation server, ticket server. Then all the buses are equipped with one or more edge devices running OSGi. In this case, they're all running Knopflerfish, and they're all connected to Ubicore, connected to the in-vehicle network. Yeah, they are connected to the in-vehicle network FMS, and you have a local network also in the buses where they're connected with through IP. I think I actually said most of these things. I'm going to skip that one. So, what makes OSGi really good for making such systems like a bus fleet system is OSGi really works as an embedded integration platform. So for the people developing the business logic, OSGi really creates a sandbox in which these services can exist, they can exchange data. You provide an API layer towards the underlying devices and FMS buses, whatever you have inside the buses. Typically, you don't want to mix, they are low level, and you don't want to really go into detail there, and you want to keep those 2 worlds really separate. So you have the application business logic on one layer, and the native, this is typically C++ code that talks to the actual devices underneath there. So this service layer is, they are logical using these devices, but they're physically abstracted, and OSGi creates this really nice abstraction layer in between the two. So if you want to talk to something connected to the FMS bus, you talk to it through a service, and that gets translated down to a FMS call, which then goes out on the bus. So usually at companies you have two different departments, one doing the business logic, one doing the low-level device integration. And having this nice separation in OSGi makes it makes it easier for them to work together and coexist, actually. A typical bus fleet would include like 5,000 buses, typically, give or take a few thousand. Each bus typically have around 5 edge devices, most of them being validators, where you beep your tickets. And each edge device typically run between 150 and 200 bundles, depending a bit about what it's supposed to do. And most of the business logic was developed using declarative services. So inside, if you look inside the vehicle, in this case you just have 4 different gateways. You have one designated communication gateway that's tunneling all the IP traffic through it. It also has the bundle cache, so that's the bundle cache. That's going to be the bundle cache for the whole bus. So when the agent requests a download, it will first look, is it available in a bundle cache? If not, go out and fetch it and put it in the bundle cache, and then I can fetch it from there. And probably my neighbors in the bus will probably use the same or need the same bundle in the future as well. Then, of course, the service app, the OSGi bundles running here that does validation, they talked directly to the validation server and the tracking server and whatever. So Ubicore, what we provide is really the provisioning and the configuration and the handling of the OSGi platforms themselves. We have not done any tracking or validation or anything else. That's what our customers typically would do. A few words of the lessons learned. I think I covered this already, that the main benefit, or one of the main benefits we see with using an OSGi solution, we've also heard this from customers, is that you get this clear separation between the business logic and lower level device parts, typically implemented in C or C++. You also get a uniform architecture. You don't need to recompile your business logic if you have a mixture of edge devices out there, and that is quite common. You could have x86-based edge devices, you could have ARM-based, or you could have MIPS-based. And it's the same business logic. From a Ubicore point of view, we don't really have to treat them that differently. And of course, it's remotely manageable, which is a huge benefit for the bus operators. Use declarative services. Base your design on declarative services when you make the business logic layer. It will force the developers to design well-defined services performing well-defined tasks. It's really a good way of designing such systems. And this is something we see quite often, that in the beginning, people don't really fully understand the declarativeness and the dynamic behavior of OSGi. So, especially in the world of devices, where you have things coming and going at a more constant, things come and go, it's natural. So if you over-componentify everything, saying this component will appear when this happens, it's actually quite easy to create service JoJos. Something happens, and then you get a number of services, and when that device is gone, they all disappear again. So it gets fluctuating service chains like this, because this depends on that, which depends on that, which depends on that. And that can be a really shocking experience for developers the first time when they experience this. So be a bit careful there. Did we encounter any problems during our developments? Yes, of course we did. OSGi is a very powerful tool, but these fantastic capabilities that OSGi brings can also sometimes actually be its worst enemy. So if you put OSGi in the hands of the crazy or incompetent developer, you can create complete mess. Of course, you can do that in C and C++ as well. But people don't fully also understand that OSGi is dynamic and it's multi-threaded. And before you fully realize that and take that into account, you can create mess, and it's not, and with this mess, the behaviors can be quite unexpected, actually. Third-party libraries. You should use third-party libraries when there are good third-party libraries out there, of course. Many of them claim they support OSGi. Many do, or often they do, but sometimes they don't. And this can create problems if they are not properly designed. And I think the world of bus fleets are not alone in this, I think. Debugging declarative services can be a challenge. We started off this with, I'm not sure if it was declarative services, one of the first versions of declarative services when we were brand new out there. And the tooling back then for introspection wasn't, it was missing some features, put it like that. So, but it has improved, and I think that the tooling for declarative services is now much better than it was. So we hit some bumps in the beginning when we did this. Inside the vehicle, you typically want to use remote in-vehicle services between the devices, and you want to kind of see this. This is my vehicle in-vehicle. This is my vehicle remote services, and they should be separate from any other remote services out there because they are my neighbors. I can speak to them. I trust them, but I don't trust this other guy sitting somewhere else. And we started off this before the spec work. I mean, the spec work is kind of still ongoing in regards to this in OSGi. So what we found here is that you really need good discovery mechanism. And in a way, these services that, if you want to call a service from that edge device to this edge device, it's a bit like this edge device, in a way, appear as a device, kind of, to that other device. Because they can, that's a way how you can actually model this. And you also need, you would need a good vehicle, like something like a vehicle services registry, and you need good remote services implementations. And here, to be honest, we don't have our own implementation. We've tried other implementations, and we've been struggling a bit in this area, to be honest. Hopefully, it will improve in the near future. So that was the world of buses. Thank you.